Hello my friends, and welcome back to Sky Creative Channel. From the world's longest suspension bridge to bridges that built themselves in mid-air, join us as we explore the remarkable engineering behind 5 extraordinary bridge projects that are reshaping how we connect our world. These aren't just structures, they're monuments to human ingenuity. There's something deeply satisfying about watching engineering dreams become reality, especially when they break world records. The Canakkale 1915 bridge in Turkey isn't just another crossing over water, it's the longest suspension bridge on Earth, with a main span stretching an astounding 2,023 meters between its towers. That's over 600 feet, folks, longer than 16 football fields laid end to end. What makes this project truly remarkable is how it bridges not just water, but continents. This magnificent structure connects Lapseki on the Asian side with Gelibolu on the European side, spanning the historic Dardanelles Strait. For those of us who remember learning about the Battle of Gallipoli in school, this strait holds tremendous historical significance, and the bridge's name, 1915, commemorates the centennial of that fateful campaign. Now, let's talk about the engineering marvel you're witnessing. Suspension bridges have been around since the 1800s, but the technology has evolved dramatically. The foundation work began with enormous caissons. Those are watertight chambers sunk deep into the seabed. For the Canakkale Bridge, engineers had to contend with challenging soil conditions and seismic requirements, given Turkey's position in an earthquake zone. NTHE towers themselves are absolutely massive steel structures, rising 318 meters above sea level. To put that in perspective, they're taller than the Chrysler Building in New York. These towers had to be built with pinpoint accuracy, we're talking millimeter-level precision, because any deviation would affect the entire bridge structure. The construction utilized climbing formwork systems and specialized tower cranes that could lift massive steel sections weighing hundreds of tons. NTHE main cables are engineering marvels in their own right. Each main cable contains thousands of individual high-strength steel wires, bundled and compacted using hydraulic presses. These cables were built using the spinning method, where a traveling wheel carries wire back and forth across the span. It's the same basic principle John Roebling used for the Brooklyn Bridge back in the 1880s, but with 21st century materials and precision. Each wire must be tensioned exactly right. Too loose and you lose structural integrity, too tight and you risk premature failure. NTHE deck construction employed a technique that would fascinate anyone who appreciates old-school engineering brought into the modern age. Rather than building out from both sides simultaneously, the traditional method, the contractors used a prefabricated steel orthotropic deck system. These deck sections, each weighing around 700 tons, were fabricated off-site in specialized yards, then transported by heavy lift vessels and precisely positioned by massive floating cranes. It's like assembling a giant jigsaw puzzle over water, except each piece weighs as much as a fully loaded 747. For lifting and positioning these enormous sections, the project deployed some of the most advanced crane systems in the world. We're talking about specialized derrick cranes mounted on the towers and traveling gantry systems that could move along the main cables. These weren't your grandfather's construction cranes. They featured computerized load monitoring, GPS positioning, and anti-collision systems. The precision required is mind-boggling. In winds that can gust up to 30 miles per hour, crews had to position deck sections within centimeters of their target location. NTHE project also utilized advanced geotechnical drilling equipment for the foundation work. Massive rotary drilling rigs, some standing several stories tall, bored down through layers of soil and rock to reach stable bearing strata. These machines use tri-cone roller bits, or down-the-hole hammers, depending on the rock hardness, and can drill shafts over 3 meters in diameter to depths exceeding 50 meters. It's impressive how far we've come from the old days of driving timber piles with steam hammers. One particularly interesting aspect of this project is the seismic isolation technology. The bridge incorporates shock transmission units and dampers that allow the deck to move independently during an earthquake while the towers remain stable. This technology has its roots in innovations developed after the 1989 Loma Prieta earthquake in California, which many of us remember vividly. It's gratifying to see how lessons learned from our own engineering challenges have been applied worldwide. NTHE construction also required sophisticated temporary works. Engineers installed a temporary catwalk, essentially a suspended walkway between the towers, to facilitate cable spinning operations. Workers walked along these catwalks hundreds of feet above the water, much like the brave men who built the Golden Gate Bridge in the 1930s, though with considerably better safety equipment these days. An NTHE project represents a fascinating blend of time-honored engineering principles and cutting-edge technology. While the basic suspension bridge concept hasn't changed since the days of the Brooklyn Bridge, the materials, precision, and construction methods have advanced tremendously. High-strength steel alloys, computer-aided design, GPS positioning, and advanced construction equipment have made possible what our predecessors could only dream about. Yet the fundamental challenge remains the same: building a structure that can safely carry thousands of people across a formidable body of water, day after day, year after year, while withstanding everything nature can throw at it. Here's something that reminds me of the great American highway projects of the 1950s and 60s, a beautiful example of modern viaduct construction on Spain's A27 highway. This particular structure, designated E1+000, sits along the Vals Mont Blanc section, and it's a testament to how far bridge engineering has advanced while still honoring the fundamental principles established decades ago. What we're looking at here is actually two parallel structures, a left carriageway and a right carriageway, each with 5 spans. This asymmetric design is increasingly common in modern highway projects, allowing engineers to adapt to varying traffic demands while optimizing costs. Now, the really interesting part is the construction method: post-tensioned pre-stressed concrete with a variable depth, lightened gullet section. Back in the early days of concrete bridge building, everything was cast with uniform depth. But engineers realized that a bridge doesn't need the same strength everywhere. You need maximum depth and strength over the piers where forces concentrate, but you can reduce material at midspan where the loads are lighter. NTHE construction technique employed here is fascinating for anyone who appreciates practical problem solving. The contractor used what's called the balanced cantilever method with form travelers. Imagine a specialized moving framework, essentially a sophisticated form system that hangs from the already constructed portion of the bridge. These form travelers, massive pieces of equipment weighing dozens of tons, incrementally build outward from each pier in segments, typically 3 to 5 meters at a time. Here's how it works. The form traveler positions itself, crews install reinforcing steel, then pour concrete for that segment. While the concrete cures, usually 48 to 72 hours, post-tensioning cables are threaded through ducts embedded in the concrete, and then tensioned using hydraulic jacks. This post-tensioning is crucial. It compresses the concrete, allowing it to span much greater distances than conventional reinforced concrete could manage. It's the same principle that made the Great Western Dam projects possible, applied horizontally instead of vertically. Pier 3, the tallest at over 27 meters, that's nearly 90 feet, presented unique challenges. Constructing such tall piers requires specialized climbing formwork systems. These aren't permanent structures, they're modular scaffolding and formwork units that climb up the pier as construction progresses, supported by the concrete that's already cured below. What I find particularly satisfying about this project is how it reflects the evolution of highway infrastructure. When Eisenhower launched the interstate highway system back in 1956, viaducts were typically built with uniform sections using simple span construction. Today's structures are more efficient, more elegant, and despite being lighter, they're actually stronger. The continuous construction eliminates vulnerable joints, the variable depth optimizes material use, and the post-tensioning provides resilience that simple reinforced concrete cannot match. It's proof that sometimes newer really is better, though the fundamental engineering principles, load, stress, deflection, remain as timeless as mathematics itself. Let me tell you about one of the most ambitious projects ever undertaken in the Arabian Gulf, Bahrain's northern Manama Causeway. Now, for those of us who remember when the original Bahrain Causeway opened back in 1986, connecting Bahrain to Saudi Arabia, this new project represents the next generation of marine infrastructure in the Middle East. NNTHE, Northern Manama Causeway, isn't just a bridge. It's a complete elevated highway system that will dramatically change how people move around Bahrain's capital region. The project involves constructing a multi-lane causeway that will relieve congestion in one of the most densely populated areas in the Arabian Gulf. NTHE foundation work for a causeway project like this is absolutely critical. Unlike bridges that span from one solid ground to another, causeways require creating artificial islands or continuous foundation structures across long stretches of water. The process typically begins with extensive seabed surveys using side-scan sonar and multi-beam echo sounders, high-tech equipment that maps every contour of the ocean floor with precision our maritime ancestors couldn't have imagined. Once engineers understand what they're working with, the real work begins. For a causeway of this scale, contractors deploy a fleet of specialized vessels. We're talking about heavy-lift barges, dredgers, and jack-up platforms, vessels that can lift themselves out of the water on massive legs to create stable work platforms. The dredging operation alone is monumental. Trailing suction hopper dredgers, essentially floating vacuum cleaners, suck up sediment from the seabed. Some of this material is disposed of at designated dump sites, but much of it gets reused for land reclamation, creating the embankments and islands that form the causeway's foundation. NNTHE pile driving equipment deployed on projects like this would be familiar in principle to anyone who worked on marine construction back in the day, but the scale is staggering. Modern hydraulic impact hammers can drive steel piles, hollow tubes up to 2 meters in diameter and dozens of meters long, deep into the seabed. These hammers generate thousands of tons of force with each blow, and the whole operation is monitored by computerized systems that track pile penetration, blow count, and driving resistance in real time. In FOR longer spans where the causeway transitions to bridge-like structures, you'll see massive floating cranes, some of the largest mobile cranes in the world. These impressive machines, mounted on barges or specialized vessels, can lift prefabricated concrete beams weighing thousands of tons and position them precisely onto pre-constructed piers. It's a ballet of heavy equipment that requires perfect coordination between crane operators, marine pilots keeping the vessels positioned, and survey crews ensuring everything aligns to millimeter accuracy. NTHE concrete work itself represents a massive logistical challenge. You can't just send a concrete truck across water, so projects like this require either floating concrete batching plants or a steady procession of barges carrying fresh concrete from shore-based plants. The concrete mix used in marine environments is specially formulated with additives that make it more resistant to salt water. Lessons learned from countless earlier projects where aggressive chloride ions led to premature deterioration of reinforcing steel. Speaking of steel, the reinforcement cages for large pier foundations and deck sections are prefabricated on shore. Imagine cylindrical cages of reinforcing bar, 10 or 15 feet in diameter and dozens of feet long, tied together by workers and then lifted in one piece by crane. It's industrial-scale fabrication that has to meet exacting specifications because once that concrete is poured, there's no going back. NTHE causeway deck construction often employs precast segmental construction, a technique that really came into its own in the 1970s and has been refined ever since. Individual deck sections, complete with embedded utilities and barrier walls, are cast in shore-based yards under controlled conditions. This ensures quality and allows work to proceed regardless of weather conditions at the construction site. These segments are then transported by barge and lifted into place, connected by post-tensioning cables that run through the entire length of the bridge, pulling everything together into one continuous structure. What I find most impressive is how this project represents the culmination of over a century of marine construction knowledge. The basic principles, create a stable foundation, build strong piers, place a durable deck, haven't changed since engineers built the first railroad trestles across American waterways. But the scale, speed, precision, and durability have improved dramatically. Projects that would have taken decades with older methods are now completed in years. Structures that might have lasted 50 years with older materials and techniques are now designed for 120-year service lives. Now here's something that perfectly illustrates how old wisdom meets new technology: the Busan-Suyong Bridge project by the Korea Expressway Corporation. This particular project is fascinating because it employs S-barch technology, a construction method that's revolutionizing how we build certain types of bridges. S-barch stands for Shifted Basic Arch, and if you've got an engineering bent, you'll appreciate why this is clever. Traditional arch bridge construction requires extensive temporary scaffolding or falsework underneath the arch during construction. Imagine building a complete temporary structure just to support the bridge until it can support itself. Anyone who's worked on or watched bridge construction back in the day remembers forests of timber or steel scaffolding filling the space beneath a growing arch. It was time-consuming, expensive, and sometimes dangerous work. NTHE equipment required for this operation is quite sophisticated. The core of the system is a specialized movable scaffolding system, sometimes called a form traveler, that hangs from the already constructed portion of the arch. This isn't some flimsy temporary structure. We're talking about heavy steel frameworks weighing hundreds of tons, equipped with hydraulic jacks for precise positioning and adjustment. These travelers inch forward as each new segment is completed, carrying the formwork, platforms for workers, and all the equipment needed for the next section. And concrete placement for each segment requires careful coordination. Mobile concrete pumps, with their distinctive articulated booms, can reach up and over existing structure to deliver concrete precisely where needed. Each segment is typically cast in stages. First, the main structural elements, then connecting portions, with reinforcing steel tied into place, and post-tensioning ducts positioned before any concrete is poured. Modern concrete mixes for projects like this include superplasticizers and other admixtures that make the concrete flow easily into complex forms while maintaining strength. NTHE post-tensioning operation is where precision really matters. High-strength steel tendons, bundles of individual wires or strands, each capable of withstanding enormous tension, are threaded through ducts cast into the concrete. Once the concrete reaches sufficient strength, typically after about a week, hydraulic jacks pull these tendons with forces measured in hundreds of tons. The tendons are then anchored, leaving the concrete in permanent compression. It's this compression that gives the structure its extraordinary strength and allows it to span distances that would be impossible with conventional, reinforced concrete. NTHE S-barch method's big advantage here is that it eliminates the need for massive scaffolding reaching all the way to the ground, which would have been a nightmare to install and would have blocked valuable urban space during construction. Let me tell you about a project that's near and dear to anyone who appreciates the changing face of North American infrastructure: the replacement of the Sombrio Bridge, located east of Port Renfrew on Vancouver Island. Now, this might not grab headlines like massive suspension bridges or miles-long causeways, but it represents something equally important: the ongoing renewal of our aging transportation infrastructure. NTHE Old Sombrio Bridge had served faithfully for 55 years. Think about that. Built back in the late 1960s, when wooden bridges were still common on secondary roads throughout North America. It was a single-lane timber structure, the kind many of us remember from rural roads, cautiously approaching, checking for oncoming traffic, then carefully crossing weathered planks that sometimes showed a bit too much daylight through the gaps. These bridges had character, no doubt, but their time has passed. NTHE construction approach for a project like this typically involves building the new structure adjacent to the old one, maintaining traffic flow throughout construction. The Sombrio area is known for its stunning natural beauty, so environmental sensitivity during construction is paramount. End foundation work involved driven steel piles or drilled concrete piers extending down to competent bearing material. Modern pile drivers are far more efficient than their predecessors: diesel or hydraulic hammers that can drive a pile in minutes that might have taken hours with older, steam-powered equipment. NTHE superstructure, the part you drive on, most consists of steel or concrete girders supporting a concrete deck. Prefabricated components expedite construction in remote locations where weather windows can be limited. Mobile cranes, probably in the 50 to 150 ton capacity range, would handle the beam setting operations, lifting each girder into place with precision that's become routine with modern equipment but still requires skilled operators who understand load dynamics and safety margins. NTHE deck construction involves forming, reinforcing steel placement, and concrete pours that must meet strict specifications for strength and durability. These refinements come from decades of experience with bridges that deteriorated prematurely because we didn't fully understand chloride-induced corrosion back when the old Sombrio Bridge was built.